Okay. Yeah, so hello everyone. Today we have Nat T from Harvard University, and he's going to talk about hybrid fracton phases. Nat is actually joining us from Thailand, where it's 3 a.m. right now. So thank you. And yeah, please go ahead and start.
Okay, thank you, Arpit, for inviting me to give a talk in the CMP seminar. So today I'm going to be talking about some recent work on hybrid fracton phases. And this is based on a paper that's already out, and then one more that will hopefully publish soon. So first of all, let me thank my collaborators, which is Wenjie and Sagar Vijay. They were both former Cambridge people in Cambridge, Massachusetts, who have collectively moved to Santa Barbara. So first of all, let me motivate by the problem by talking about topological order, which is gap phases of matter which have fractionalized excitations. And these topological orders, as we know, are really important. There are new phases of matter that have ground state degeneracy that depend on the topology of the underlying manifold. And we also believe that at low energies, these states can be described with topological quantum field theory. And some examples of these states that, as people know, are, for example, fractional quantum Hall states. And then there are also some more toy models, for example, the Kitaev torque code, or this resonating valence bond solid, and other quantum spin liquids. But recently, people have discovered a new type of order, which is called a fracton order. And these seem to be a new type of gap phase of matter. At least we believe they cannot be described by topological quantum field theories. And the characteristic property of these phases is that the emergent excitations have restricted mobility, in the sense that you might have particles that cannot move on its own, but you might be able to move it if you move them collectively. For example, you cannot move a single particle, but it may be possible to, say, move a dipole of such an excitation. Or in some cases, as in Haas code, which was discovered here in Caltech, you cannot even move any amount of excitation. So a single excitation is immobile, and a pair of them is also immobile. And another feature of these fracton orders is that they have robust ground state degeneracy, which scales with the system size. So in the two slides, I've introduced topological orders and fracton orders, and though they sort of have some key properties, that they have some ground state degeneracy, which is robust to perturbations, there are some differences. So, for example, in topological orders, all the excitations are mobile in the dimension they're defined in. So in a 3D phase, all the particles or excitations can move freely in 3D. But in fracton orders, they're mobile. And on the other hand, topological orders have a ground state degeneracy that does not depend on the geometry. It only depends on the topology you put it on. Whereas fracton orders seem to have a ground state degeneracy which scales with the system size. That is, there is some geometric dependence on the order. So one might wonder if there is a nice way to connect the two, whether topological orders and fracton orders can have sort of like a unifying prescription, because at the moment they seem to have sort of like different properties. So in the past couple of years, there have been some efforts in doing that. And what people found was that by starting, for example, with lower dimensional topological phases, you can take a stack of them and do some strong coupling in order to enter either, for example, a 3D topological order or a fracton order. So for example, you can start with 2D stacks of a stacks of 2D Z2 toric codes and perform some condensation of charged particles in every adjacent layer. And what you end up is you end up in the 3D toric code phase, Z2 toric code phase. And another example is the so-called p-string condensation, where if you start with stacks of toric codes and you condense a so-called p-string, which is a collective of excitation of like these fluxes. And if you do this condensation, it turns out that you can also enter a Fracton order, for example, the X cube model. But you can sort of enter either phase, but it still doesn't give you a connection to see between the two phases. And other relations that people have come out with recently are lattice models which have non-abelian Fracton excitations. And what they found is that in these constructions, you have non-abelian Fracton excitations, but you also have mobile excitations, and they live together, and you cannot separate them. So these are just a couple of papers that came out in the past 2 years, and that have touched on this topic. But I guess, at least to me, I found the non-abelian one quite a bit hard to penetrate. And so we were wondering whether there was a possibly easier toy model to analyze so that we can sort of build or get more intuition from these phases that have both mobile and immobile particles living together. And so that is what we address in this work. So in this work, we realized a abelian sort of hybrid between a topological order and the Fracton order. And I will demonstrate that these two orders coexist and you cannot separate them. So for example, if I talk about the 3D toric code, you might have a charge excitation, which is a mobile point charge, and you can have a Z2 flux loop excitation. Whereas for the X cube model, the charge is a Fracton, it cannot move, whereas the flux is a line-on. The name just means it can move in one dimension. And of course, you can take the 3D toric code and just stack it with an X cube model. But in that sense, it's just a tensor product of the two, and that is not as interesting. But the model I will introduce today has the following property. So the excitations can be labeled in the same way as X cube and toric code. So you have a Fracton, a line-on, a mobile point charge, and a loop. But however, it has different fusion and braiding rules. So for example, in the hybrid between the toric code and the X cube model, we find that if you take two Fractons and fuse them together, usually in the X cube model, if you take two Fractons and fuse them together, it just becomes a vacuum. But if you take two Fractons and fuse them together in the hybrid model, you end up with a mobile charge, which is like the mobile charge in the 3D toric code. And on the other hand, if you take the mobile flux loop and take two of them and fuse them together, usually in the pure 3D toric code, that'll get the vacuum. But in this case, you get line-ons, a bunch of line-ons. And these line-ons live at precisely where the corners of this mobile flux loop is. And furthermore, usually in the 3D toric code, you have a braiding phase of -1 when you braid the point charge around the flux loop. But here, since the point charge is a fusion of two Fractons, you can actually braid the flux loop around the Fracton, and that gives you a phase of I. And of course, you can see that in the stack model between a toric code and X cube, such a braiding does not exist. So that shows that the model we have is different from a stack, just a stack between the 3D toric code and the X cube model. Okay, and so to just give a summary of the main results that in our work, you can take for the paper that's already out, you can take your favorite Fracton model, for example, X cube or Haskell, and you can create a hybrid with the Z2 Tor code. And what happens is that the fusion is such that the charge Fracton excitation can fuse into a mobile Z2 charge, and the flux loop can fuse into the flux of the Fracton model. And so that is the Boolean version. And in this talk, I'm going to focus on two main examples. One is which we call the hybrid Tor code layers. This Tor code layer is just like a toy model of fractons where you have a stack of 2D topological orders. And then I will first talk about this one to build some intuition. Actually, a lot can be said just by looking at stacks of 2D topological orders and forming some condensation. And then later I'll move on. After we build intuition, I'll move to talk about the hybrid between X cube and the Tor code. Right. And if time permits, I will talk about some forthcoming work, which is a generalization of the abelian case here into a non-abelian case. And in particular, we construct a quantum double sort of analog of hybrid Fracton orders for any finite group G that has an abelian normal subgroup. And what we actually find is that the examples of gauging of non-abelian fractons that have been discussed previously can all fit into this picture. And we can also realize other fractons with non-abelian group that cannot be realized in such procedure as well. Okay, so let me take a moment to see, are there any questions before I move on? Okay, if not, then let me go on and introduce the model. So I believe many of you are probably familiar with the lattice model for the Tor code and X cube, but just for the sake of setting up the terminology and the lattice, let me just review it really quickly. So the 2D Tor code, I can define it on a square lattice. And here I will use the notation of a red edge being a poly X operator and the blue edge being a poly Z. And for the Tor code, there are two terms in the Hamiltonian. One is the vertex term and one is plaquette term. And the vertex term, of course, is composed of 4 poly X operators on the edge surrounding that vertex. And the plaquette term consists of 4 poly Z operators on the edges surrounding the plaquette. And this is a commuting projector model because all the terms commute, so you can exactly solve it and find the ground state. And the excitations are topological in the sense that you can only violate a pair of these vertex term or plaquette terms at a time. So for example, if I use a string of poly Z, then I can violate this vertex term at 2 positions. And that's what I'll call as the charge excitation E. And that just means that the eigenvalue of this vertex operator is -1 there at that point. And on the other hand, if I use a string of poly X on the dual lattice, I can excite 2 flux excitations, which I'll call M. That's the 2D Tor code. And for the 3D Tor code is very similar. You just define this on a cubic lattice, and you just have these extra edges now for the vertex term. And there are other plaquette terms for the other plaquettes on the cubic lattice. And now the excitation of the charge excitation is also just a point particle. It can now move in 3D, but the loop excitation is now, the flux excitation is now a loop, because when you excite with a membrane of these poly X operators, you can only excite a loop excitation, which is a violation of the plaquette terms all around this loop, which is the boundary of the membrane. And finally, just to set the terminology, let me describe the X cube model. And the lattice I'll choose for the X cube model in this talk is that I'll choose the vertex term to be a product of 12 poly X operators. Now, the poly X lives on the plaquette of the cubic lattice. And the vertex term consists of 12 poly X's where for the 12 plaquettes surrounding the vertex. And now the flux term are cube terms, and there are 3 of them. If you pick a cube, you can apply poly Z on the 4 sides of the cube, leaving out the 2 edges, which are in the X direction for this one, for the Y direction, and for the Z direction. And note that all these 3 actually product to the identity. So actually only 2 of them are independent. And the topological excitations of this model is if you excite a charge, you can use a poly X acting on a membrane. And you notice that just one of these excitations, which is a violation of the vertex term, is a fracton, because you cannot move it in the sense that you can only create 3 other fractons if you want to hop it. However, if you have a pair of them, then you can actually move them. If you have a dipole like this, you can actually move them in the direction perpendicular to the direction of the dipole. And for the fluxes is a line-on. This name just means that it has 1D mobility, and it is a violation of the cube terms. And how do you excite that? You can excite that using a rigid string of poly X operators on the dual lattice, and that excites 2 cubes, and that excites the line-ons. And the mobility of the line-on I've depicted with the double arrow here. Okay. So what I want to do right now is to warm up with the simplest, I guess. It's not, I guess it depends on your terminology. It's a 1-foliated fracton order. So in the sense of terminology of fractons, what I just mean is that suppose I take a stack of Z2 toric codes, then it sort of have some fracton phenomenology in the sense that the excitations can only move in the plane they're defined. You cannot move these anyons between planes. And furthermore, the ground state degeneracy scales with the system size, because it's just 4 to the number of layer of toric codes you have in this case. So you can sort of view this as like the simplest type of fracton order. And now what I want to do is I want to create a hybrid version of the 2D toric code stacks and the 3D toric code. So what will result is that I will have charge excitations, which are planons. They can only move into planes in their respective planes. But when I square them, I get a mobile charge that can move in 3D. And on the other hand, I have a loop excitation of the 3D toric code. And when I square it, I will get a bunch of planon excitations, and I'll show how this arises in the lattice model. Okay. So first, let me, to motivate the construction, let me point out first that actually you can construct the 3D toric code by using 2D stacks of Z2 toric codes, and that was pointed out by these folks here. And what they realized is if you take a stack of Z2 toric codes and you condense a pair of E particles in every adjacent layer, then first what happens to the E charge? The E charge now after the condensation, the E charge in every layer now just becomes the same particle. So in that sense, it allows the E to move between the layers. So now after the condensation, E is a fully mobile particle in 3D. And on the other hand, the flux excitation M in each layer is confined because it braids non-trivially with the E particle. But you might wonder if there's any flux excitation left. So in fact, if you take a loop of this M, that is, if you take a loop excitation created by stringing the M excitations in all the layers, then you actually find that, for example, this part of the loop here, MM, commutes with the condensation EE. So this loop excitation actually survives the condensation. And what I've shown is that you have a mobile E particle and you have an M loop. And so that is basically the 3D Z2 toric code. So moving one step from this, what I'm going to show is a similar condensation, but after, in the end of the day, we'll get hybrid toric coat layers. So now let me show you a similar construction. I will now take the Z4 toric coat, and the charge excitations in each layer are just 1 E squared E cubed, and the flux excitations are 1 M squared M cubed. Now what I do differently is that if I just condense pairs of E and E bar in adjacent layers, then at the end of the day, I'll get a Z4 3D toric coat. But what I'll do here is I'll instead condense E square between every layer, every adjacent layer. So what happens? The E particle is still for the E particle in each plane is still in different superselection sectors. But now the E square particle becomes the same particle after condensation. So the E particle is still a planon, but now the E square is a fully mobile excitation. And on the other hand, let us look at the flux excitations. The fluxes M and M bar are now confined. But if you construct a similar loop of M and M bar as shown here, then by stringing M and M bar in the way shown, this loop actually commutes with the condensate. So in the end, you get out an M loop that survives that remains deconfined. And also note that the M square flux commutes with brays trivially with E square, so it still remains a deconfined excitation. So what we see is that now the fluxes, if you have the M loop here and you fuse two loops together, what happens is that it becomes just a string of M square particles, but the M square particles is a planon excitation, and each can now move freely within their respective planes. So that is, by doing this condensation, we find that we can obtain the phenomenology of the hybrid toric coat layers that I introduced verbally earlier. Okay. So to realize this in a lattice model, we can actually do the following. So if you take the stabilizers or terms in the Hamiltonian for I'm going to take the terms in the Hamiltonian for the 3D toric coat and the 2D toric coat, but I'm going to modify them a bit. So on the X and Y edges, I'm going to replace the Z2 variables of poly X and poly Z with a Z4 qubit, and I'm going to put a generalized Pauli on that edge. And this modification is made such that if I now take the vertex term of the 3D toric coat and square it, I will get the vertex term for the 2D toric coat. And now, on the other hand, if I take the plaquette term of the 2D toric coat and square it, there's only the XY plaquette in the 2D toric coat. If I square it, I will get the plaquette term of the 3D toric coat in the XY plane. So after this modification, one can actually show that you can set the excitations, and you can find that the phenomenology is exactly what I've described. You can excite a planon, which is E, which is a charge excitation, using a string of this generalized poly Z. But if you square it, then you can actually move this charge 2 excitation in the third direction. So it's completely mobile. And on the other hand, if you have a flux excitation, if you use generalized poly X's, you can excite this loop excitation. And then if you square it, only the plaquettes that I've shown in purple and cyan will remain violated. And then this just decouples to excitations of like the 2D toric coat, which is a planon. So after you square it, you only be left with these 4 excitations. And then now each of these planons are now free to move within their respective planes. And so that is exactly the phenomenology that I've shown by arguing formally using this condensation. Okay, So are there any questions up to this point?
I have a question.
Yes.
When we talk about the fusion in the 2D topological order system, where the charge or the flux we talk about is correspond to the supersaturation sector of the
Yes.
system. So we are talking about the
Yeah.
fusion of combining two supersaturation sector. But here, when you talk about the fusion of two loop to the linen, can you also correspond this to some kind of generalization of supersaturation sector?
I mean, the loop here belongs to one superselection sector, and when if you want to write it formally, it's just that when I take two of these quote unquote M loops and fuse them, then I get a product of M squared in all the layers where this loop is defined.
Yeah, but if you consider just two loops of finite size, they are just belong to the same sector as the vacuum sector. So maybe
that's for the Z2 torque code, yes. But in this hybrid model, that's not the case.
So you cannot create a small loop from the vacuum.
You can.
Yeah, so
it
is just the same sector as the vacuum.
Right. But I'm saying if I have two loops and I fuse them together, I don't get the vacuum. So this M loop is actually as Z has order 4. It does not have order 2 in the hybrid model.
Okay.
So in the same way, the planon has order 4 now. So the planon is a charge excitation of the 2D torque code, but now after the hybridization, it's now a Z4 excitation.
Okay, thank you.
Yeah.
I have a quick question for your degree of freedom. So you have a Z4 poly in each plane and a Z2 poly on vertical leg, right?
Only on the X edges, yes.
Okay, so can you make it isotropic?
Can I make it isotropic? Well, this model is not isotropic to begin with because I've these E excitations, for example, they can only move in one plane, right? So it's it's not isotropic to begin with.
I see.
Yeah. Any other questions?
Yeah, so
right.
I think you were saying that this hybrid kind of M loop is you can create it from vacuum, but using some local operator. But here it's so you can create a small hybrid M loop of this kind, right? Is that your point?
Yes, using this operator here.
Okay, and if you combine them together, you get these M squares.
Yes.
So basically, you can create those M squares directly from vacuum, right? I think
you could have, just this is enough. In one plane is enough.
Yeah.
To create these M squares.
No, I mean also across the layers, because
you
get after
you can do them separately.
Okay.
Sort of, you're not forced to have them be all vertically stacked on top of each other. Each of them can move freely on its own.
Right. Okay. Thanks.
Okay. Yes. So let me move on, I guess. So here this example was to sort of build intuition for the X cube hybrid version that I'm going to present. And so basically the change is that instead of thinking of 2D toric code stacks as a Fracton model, I'm going to now move up to X cube. And now the only change is that instead of the E's and M squares being planon excitations, meaning they can only move in planes, now the charge and fluxes become those of the X cube. And so we'll see that two fractons can fuse to a mobile point particle, and a mobile loop can fuse into a bunch of linons. Okay. So the exactly solvable model might be a little daunting, so let me try to break it down step by step. So for this model, we are on a cubic lattice, and we define additional edges on this cubic lattice. So for each plaquette, I add this specific diagonal edge. So notice that I add only one of them and not two of them. So there's a specific orientation of edges that I'm adding here. And the Hamiltonian is the following. You can think of these terms as stabilizers of the model, non-Pauli stabilizers. But first of all, suppose I just had the vertex term here as Pauli x's on all these links, and I have for each triangular plaquette, I have Pauli z's on this triangle. Then these two just form the 3D toric code stabilizer. And on the other hand, if I had a product of Pauli x's on these plaquettes around the vertex, and these were Pauli z's, then these two stabilizers would just describe x cubed. And now I want to hybridize such that now the vertex term of the toric code will square to the vertex term of the x cube, and the cube term of x cube will square to a bunch of plaquette terms of the toric code. And it turns out that if you write down the following modification, if I just change xe and to this modified operator, which I'll use this Greek equivalent xe, and z to zeta, then it turns out that this exactly happens. And you can check explicitly that this exactly squares to this, and this cube term squares to a bunch of plaquette terms of the toric code. And I'm writing this explicitly for you to see, and it might look daunting, but it turns out that these new operators C and zeta, they actually satisfy simple algebra. So if you restrict yourself only to the edges, then C just acts like the usual Pauli X. It anti-commutes with Z. And if you restrict only to the plaquettes, zeta just also acts like Z to Pauli Z to Pauli Z, and it anti-commutes with XP. However, zeta and Xi have a non-trivial commutation relation as follows. The zeta and Xi will only anti-commute if E is contained within that plaquette, and they only anti-commute up to a phase of I or minus I. So this is a simple algebra, and you don't need to look at the definitions and all, and you can just use this as your working definitions if you want to, and this is sort of enough. Okay, and it turns out that these four operators, Pauli Z, Pauli X, and the modified ones, completely give you the operators that are needed to excite the excitations. So for example, if I use my modified zeta now to on a sheet, then what happens is I just excite 4 fractons at the boundary. And the Pauli Z, as usual, on a string excites this mobile charge. And the Pauli X, as usual, on plaquettes, excites this line on. But these modified operators, if you just use them as you would in the usual XQ or toric code, they would excite the fracton excitation and the corner excitation, and the loop excitation explicitly. Okay, but there's one interesting thing to note is that if I excite a loop excitation created using these modified operators CE, it turns out that in addition to the plaquette terms of the toric code being violated, I also have that the cube terms are violated, but only at the corners, and they have eigenvalue plus or minus I. So that's something quite interesting. And one way to see what's happening here is that usually the cube term being -1 just means that this violation is a line on. But now having an I is as if this corner of the M loop carries like half a line on, and I'm just saying that very non-rigorously. But what it implies is the following non-trivial fusion. So if I take two M loops and I fuse them together, it turns out that at the corners of the M loop, I will obtain a line-on excitation. So for example, this M loop has 4 corners, and after I fuse them, I'll be left with a line-on excitation at the 4 corners of this Q. And you can also check that a more complicated loop, wherever you have corners, when you fuse them, it'll result in line-ons. So that's sort of what I meant by this line-on. The corner carrying half a line-on. When you fuse them, you obtain a full-fledged line-on, which is now a valid excitation of your model. Okay. Right. So another interesting consequence of having this weird fusion is some interesting braiding. So usually in the X-cube model, if I have 2 fractons, I can form a fracton dipole, and that can move in the direction perpendicular to the plane. So you can form the following braiding process. So if I take a fracton dipole and a line-on which lives in the same plane, I can braid this fracton dipole around the line-on, and I can get a statistical phase of -1. But now, since we know that the corner of the M loop carries half a line-on, it turns out that if you take this fracton dipole and braid with the loop, it's possible to get a factor of I. And sort of the way to see it is actually that if you think about the trajectory swept by E and E bar here, you'll find that it'll only get a factor of I if this fracton dipole braids with the corner of the loop. So in this configuration, you see that only E forms a link with the loop, while the E bar just goes outside and does not form the link with the loop. So indeed, if I have this fracton dipole and I braided with this part of the loop instead of the corner, then both of them, E and E bar, will form a link with the loop, and each will gain a factor of I here and minus I here, and that'll cancel. So it's quite interesting to see that only this dipole can only braid with the corner of the loop, and giving you a statistical phase of I. And it's also consistent with the fact, as I mentioned, that because by fusing 2 loops together, you get a line-on. After you fuse, if you have 2 loops here and you fuse them, then the statistical phase will be just double that, which is -1. Okay. Any questions about the fusion and braiding here?
How essential is the diagonal edge in your construction when you consider
yes.
the braiding and fusion?
Right. So it's not really essential, but what is nice of having this diagonal thing is that so we don't need to attach projectors. So all these terms actually commute without attaching projectors. So that's the nice part. So if we did it just on a pure cubic lattice, then there's an ambiguity of whether you write a plaquette term going this way or going that way. So just for technical reasons, we added this diagonal edge, and it made the algebra just work out more nicely. But yeah, but it's not essential. Yeah, thank you for asking.
So even if you add a projector, you will get the same kind of fusion and braiding rule.
Yes. Right. Okay. It's just that to write out the excitations is more cumbersome. Here, I can excite everything using these operators alone, and I don't need to care about projecting to the right subspace.
Okay.
Yeah. Thank you for asking. Any other questions about fusion and braiding? If not, then let me mention briefly about ground state degeneracy. So in this model, as I mentioned, since all the terms commute and they all these operators just square or to the fourth power is just 1. So I can calculate the ground state degeneracy pretty easily, either by just counting the constraint that these projectors impose on the whole Hilbert space and seeing what's left over. Or one can also explicitly construct these logical operators or non-local Wilson operators, which are just tunneling different excitations around the torus. And by doing both, we find the same answer. And it turns out that these Wilson operators just factor into 2 sets. One is the same set as the X cube, and one is the same set as those of the toric code. So we find that the ground state degeneracy of this model on this torus, on a torus, is just the product of the ground state degeneracy of X cube and toric code. So it's perhaps surprising that the ground state degeneracy is the same, but the fusion and braiding is actually quite different. So the ground state degeneracy alone is not enough to tell the 2 apart. By the 2, I mean this hybrid model and a simple stack between X cube and toric code. And lastly, about this model, let me just mention that we can also argue that this hybrid X cube model is a parent state of both the toric code and X cube in the following way. So I can either condense by adding perturbations to the Hamiltonian. This form is just a simple magnetic field. I can either condense the E square excitation or the M square excitation. So the E square is a mobile point and the M square is the line-on. So for example, if I condense the line-on just by setting this term to infinity and figuring out what the resulting model is from perturbation theory, you get that in this limit, you sort of see that you condense the line-ons and sort of the fractons get confined. So what you're left is just the point in the loop, which is the toric code order. And similarly, if you condense the charges, then you sort of kill the excitations of the toric code, and then you enter the X cube order. Okay. So that is a nice property of the exactly solvable model we have. Okay. Yes.
Can you imagine condensing some of these loops?
Yeah, if you condense the loop, then actually I think you just enter a trivial phase because everything, you condense all the fluxes and then all the charges are confined also. So you just directly enter a trivial phase. Yeah.
I see.
Same for the fracton as well. Yeah, because they're the root excitation of this model. Yeah.
Then there's nothing, I mean, fractons are fractons, so there's nothing like kinematically constraining them being condensed or.
How I arrived at this model, it sort of might seem unnatural. Like, how would you sort of figure out how to couple the toric code and the X cube in such a way that the terms here square to this and this term here squares to that? That is, of course, not the approach we took, but just a result. So now let me try to explain how we derive these models. And the way we derived it was we start with a Z4 paramagnet, and this Z4 paramagnet has a particular symmetry. It has a Z4 global symmetry, but it also has a Z2 subsystem symmetry. And this Z2, in this case, for the X cube model, we define it to be a Z2 symmetry, which flips the spins of every single plane individually. And note that the Z4 and Z2, the Z2 is actually a subgroup of the Z4, so they are not independent symmetries. In particular, if I take all the Z2 planar symmetries and product them together, then I get a Z2 global symmetry. And this Z2 global symmetry is a subgroup of the Z4. And now the way to derive this hybrid X cube model is that starting with the Z4 qubit, we actually break it up into 2 Z2 qubits, which I denote here as orange and green. And we first start by gauging this Z2 subsystem symmetry. And that sort of maps this Z2 qubits from the vertices to the plaquettes. And the resulting model is the X cube model. But what you obtain is that you still have a global Z2 symmetry, because I've gauged away the Z2 subsystem symmetry. I only have a Z4 mod Z2 symmetry, which is a remaining Z2 global symmetry. And this Z2 global symmetry actually enriches the Fracton model in the following way: that if the Z2 global symmetry fractionalizes on the Fracton excitation, which means that if I define the symmetry action locally on the Fracton and I act with the Z2 symmetry twice, then I get a -1 sign. So this Z2 global symmetry, because of the non-trivial structure of these interplay between global and subsystem, this Z2 global symmetry fractionalizes on the Fracton. And after I gauge the Z2 global symmetry, I will arrive at this hybrid Fracton model. Okay. So this is the way we derive our hybrid X cube model. And you can also see that if I just change the subsystem symmetry to, say, some fractal symmetry, then you can also derive a hybrid Haas code as we present in the paper. So you can start with your favorite subsystem symmetry and just follow the gauging procedure to derive your favorite hybrid Fracton model. Okay. Now, since we're almost out of time, let me just briefly mention the construction for a general group. So this, I've started here with a particular global symmetry and a subsystem symmetry. But actually, this can be generalized to any finite group G and an abelian normal subgroup N. And the result of this hybrid model is that we obtain a hybrid between a Fracton model with gauge group N and a 3D quantum double model with a gauge group Q, where Q is the quotient group after of G by N. So the story is quite similar. You start with a symmetry, which is a G global symmetry and N subsystem symmetry. And for some special cases, if the normal subgroup is trivial, then you will just get the quantum double model with gauge group Q, which is equal to G in this case. And if the quotient group is trivial, you just get the usual Fracton model with gauge group N. But here we're interested in the case where both N and Q are the normal and the quotient subgroup are non-trivial. So the procedure is schematically is I start with a G paramagnet and I break this G qubit or G degree of freedom into a Q degree of freedom and N degree of freedom. And first I gauge the N subsystem symmetry and I obtain a symmetry enriched Fracton model. This Fracton model has the gauge group N. So it's, for example, XQ with gauge group N. And it's enriched by the Q symmetry. And the way the Q symmetry enriches this model can actually be determined by the group extension. So if you know about the group extension, then there's a certain data that goes into extending a group called a factor system. And this just realizes the symmetry enrichment. There is a certain map from Q to automorphism at N, and that realizes permutations. And you can also realize for a choice of co-cycle, you can realize symmetry fractionalization. And after gauging this Q global symmetry, you can obtain the hybrid Fracton model. So just to flash what the final gauge theory, if you want to say, looks like, we will have a vertex term for every group for the group G, and that is composed of a sum of A, which follows the group law of G. And you also have some gauge constraint with their delta functions, which enforce the fluxus condition and for the cube terms is for the normal subgroup N, and for the plaquette terms, it is the quotient group Q. And we verified that in the special cases that I mentioned, it does reduce to the 3D quantum double model and the Fracton model with gauge group N. And so actually to see that the charge, you can see that the charge excitations are violations of this A term. And because of this group structure, they have to transform as irreducible representations of the group G. And so if, for example, G is a non-abelian group, then you can also get non-abelian fractons because, and well, this depends on this non-abelian being a fracton does depend on what choice of normal subgroup you choose. Yes.
Ned, I have a quick question. Can you go
Yeah.
back to a previous slide?
Mhm.
So I'm wondering when did you make the choice of this omega and sigma? So when we split the GQD into QQD and NQD, did we already specify these two data?
Yes. So if you started with N and Q, if you want to reconstruct G, you need to provide these two data.
Okay, so once we make this choice, so gauging the N subsystem and Q global symmetry is just the standard way. We don't need to make any other choice anymore.
Yeah. Mm-hmm. Right.
Okay, thank you.
So all this data is actually encoded in just choosing a global symmetry G and an N subsystem symmetry. And this secretly has knowledge about Q and then these two already. Yeah.
Nat, I have a question.
Yes.
So you said that some of the irreps of G become fractons, right?
Yes.
But I thought the procedure you described is basically you start from like some kind of X cube type model for the N, and you gauge a global symmetry of that system.
Yes.
Right. So I would.
Yeah, you can start from this step.
Think that the fractons all somehow come from this X cube N X cube system. Do you mean that maybe the choice of omega makes some of them non-abelian?
Yeah, it can either be the permutation that makes them non-abelian or this fractionalization. Yeah, it can come from both.
Okay, I see.
But in the previous work that people have constructed, all the examples come from permutation.
Yeah.
So for example, as gauging this 2 copies X cube with the swap is purely permutation. So actually we can also construct models that cannot be constructed by just gauging some permutation symmetry. For example, the quaternion group cannot be obtained by a split extension in the group extension lingo.
Yeah, I see. But this is probably not relevant for my main point, but I think quaternion, right? But dihedral you can actually.
Dihedral you can, yes. Let's see. I have 5 minutes, so maybe I can flash an example for dihedral. So for dihedral, actually, there are many choices of normal subgroup you can choose. And depending on the choice of normal subgroup, the final theory all has a non-abelian D for fracton, but the other charged particles are mobile or immobile depending on this choice of normal subgroup. So in fact, the gauging of X2 copy of X cube, this work is this normal subgroup. And in fact, the defect construction, they constructed another, in the defect construction paper, they constructed another model with D4 fractons, but actually that corresponds to another normal subgroup. And then there is also a third model which one can construct with this other normal subgroup, which we haven't found in the literature yet. Yeah. Okay. Right. So let me conclude. So as I've shown, we've constructed a family of hybrid fracton orders. That is a hybrid of a topological order and a fracton order. And that sort of gives a unifying picture that actually topological and fracton orders can appear together. And in some cases, they're inseparable. So maybe that gives that sort of implies a possible unification of the two orders as one unifying picture. And we've shown the simplest case, which is abelian. And in a forthcoming work, we also construct this for any non-abelian group. So this sort of gives like a quantum double model for hybrid Fracton orders. There's some open questions, and just maybe a little technical, but one can ask whether these hybrid models have foliated Fracton order. That is, whether you can foliate out some toric code layers. And surprisingly, we think that that's not possible for the hybrid toric code layers. If you're interested, you can maybe ask me afterwards. And other aspects are possibly a twisted version of these hybrid Fracton models. Since one has loops and fractons coinciding, maybe one can think about better error correcting codes. And I guess another aspect is whether one can realize a field theory description. And we've started thinking about this field theory description a bit. Yes, so let me leave it at there, and thank you.
Okay. So maybe I can ask one question. So do you have a defect network construction for these general hybrid Fracton models, like with the?
No, we don't know how to do it in general yet, but we do know how to do it for any finite abelian group. But yeah, constructing from the defect network, we haven't thought about that at all.
Okay. Are there any other questions?
Hi, Nat. That was really cool. Thanks. Comment and a question, or maybe it's two questions. I guess so. First, for the field theory, I had this paper this summer about foliated quantum field theories. Do you think that would be a good fit, or have you just not had time to check it out yet? It seems reasonable.
I've looked at your paper a bit, but I'm not quite sure how to fit the. Yeah, I guess one has to modify add another copy of the toric code and sort of couple it in some way. Yeah, but I haven't thought that much about it. I've only been thinking about the field theory from your previous one with Yongbak, that other field theory. Yeah. By coupling that with a toric code.
Yeah, that would be harder. I think my most recent paper would be the easiest, because you could just probably add another BF theory and then set some of the level coefficients to 4 instead of 2. And then some of the other coefficients might be 0 to not completely make them fractonic. So I think it's just a matter of adding more copies and setting the level coefficients to 0, 2, or 4.
Yeah, that would be interesting to looking into. Yeah.
And of course, I have to ask about your first bullet point. Why don't you think it can be foliated?
Right. So let me go back to the so it's sort of like there's a sort of a problem in foliating. So you could think there's two things I can think of foliating out: the Z2 toric code or Z4 toric code. So the Z4 toric code, I can't quite foliate out because I already condensed stuff. So it's sort of like each layer is not really a Z4 toric code anymore. But then to foliate out the Z2 toric code, we looked at the logical operators in this model, and it sort of is coupled to this loop excitation, which goes through all. There's a membrane excitation which goes through all the layers, and they sort of don't form a Z2 toric code like a logical operator. They sort of form some weird Z4. So yeah, it seems weird, but yeah,
I see.
So I'm not sure if that's a satisfying answer.
So more generally, do you think there is any kind of RG you can do? Some sort of bifurcating RG? Yeah,
I haven't thought from the RG perspective yet. I guess the best way to think about it is to go to this sort of coupling of the symmetries, where you have this Z4 global symmetry and Z2 subsystem. Yeah, but I haven't thought much from that perspective yet.
I see. Because
surprising,
go on.
yeah. Oh, but in the three foliated case, we find that the logical operators just decouple. So actually, in this case, I think it can be foliated. But for the one foliated case, we think it cannot be foliated. So yeah, so that's something surprising to at least to us.
Yeah, if the first example can't be foliated, that would be pretty interesting because that would seem to suggest that there is no bifurcating RG, which would mean that we don't know how to do RG. And there are some other examples where we don't know how to do RG, but they're more complicated.
Yeah.
Practicos models are another example. But this example is actually quite simple. So if this example already
Right.
if we can't do RG on it, that would be pretty interesting.
Yeah.
But what happens if you like just start with these different layers, let's say on the ungauge side, and so for example in X cube, right? If you ungauge it, you have these different layers of the subsystem symmetry, and then you do a C naught between them, and you can get rid of you can separate a layer from the subsystem symmetry group. And that tells you that on gauging, it will correspond to like extracting a layer of code out. So
yeah, I mean, that's probably the way to proceed. But yeah, I haven't thought about that yet. This is just like something we'd noticed. Yeah, it would be interesting to think more about this.
Yeah, the reason I'm just mentioning it because on the ungauged side, like you can just think of a paramagnet, and so you just need to focus on the subsystem symmetry group.
Right.
And there should be some analog of this, like just doing a C naught, maybe not, but
yeah, I don't know. Maybe there's some obstruction to doing the C naught for Z4. I need to think more about it.
Okay. Are there any other questions?
Now, feel free to email me if you have questions about the QFT stuff. It might be interesting to think about.
Yeah, definitely.
Okay, feel free to stay back, but let's thank Nat for the great talk. And
thank you.
with that, we end the seminar. Thank you.